A proton moves along the positive x-axis with a velocity of 1.0 times 10 to the 7th meters per second. As it passes the origin, what is the magnetic field at the following points? This is part C of our example, in which we are going to determine the magnetic field at the point with an x-coordinate of 1.00 millimeters, a y-coordinate of 1.00 millimeters, and a z-coordinate of 0 millimeters. So now let's do our final part. We have to find the magnetic field at a point in the xy plane. I will call this point C. Point C has the coordinates of A, 0, where remember, A is just equal to 1.00 millimeters. We're going to use the Biot-Savart Law again. The Biot-Savart Law says that the magnetic field at point C is equal to mu naught over 4 pi q v, and I'm going to use just my right hand rule to find the direction of the magnetic field. So I'll write qv sine of theta between v and our point C, and then this is over rc squared, so that's the distance to point C squared, and this is going to be the direction given by the right hand rule, which we'll have to determine. You probably can guess already that the direction will be in the positive z-axis, because when we apply the right hand rule at point C, we would get a concentric circle that is centered about the positive x-axis. This is because when we apply our thumb in the direction of the line of velocity and we curl our fingers around the line of velocity, our fingers creates a circle around the line of velocity, and the orientation of our fingers give the orientation of our magnetic field lines, and at point C on our circle, the magnetic field is tangent to that point. So the magnetic field at point C will be in the positive z direction. So I'll just go ahead and put a k hat right here as a reminder. Well, in order to get our answer, we're going to need to know the distance between our source charge and point C. So that distance will be given by this vector right here, r sub c. And r sub c vector has an x component equal to a because it goes a along the x-axis. And it's going to have a y component equal to a as well. So we have a I hat plus a j hat. Well, we need the distance to point C. So the distance to point C is just the magnitude of vector C, which ends up being equal to a times the square root of 2. So now we have everything we need. We have the magnetic field at point C is equal to mu naught over 4 pi q v. Oh, well, we need to know the sine of the angle between the velocity and point C. So let me go ahead and write sine of the angle between the velocity and point C over the distance squared. So this is over a root 2 quantity squared in the positive z direction. Well, if we look at this, the angle between the velocity vector and the relative position vector is equal to 45 degrees. And we know that the sine of 45 degrees is root 2 over 2. So we could write that the magnetic field at point C is equal to mu naught over 4 pi q v. This is going to be the sine of 45 degrees. And we set the sine of 45 degrees is root 2 over 2. And this is over a times root 2 quantity squared in the z direction. So the magnetic field at point C is equal to mu naught over 4 pi q v root 2 over 4a squared k hat. Well, let's plug in our numbers. We have mu naught, the permeability of free space, is 4 pi times 10 to the minus 7 Tesla meters per amp over 4 pi times Q, which is the charge of a proton, 1.602 times 10 to the minus 19 coulombs, times the velocity, which is 1.0 times 10 to the 7 meters per second, times root 2 over 4 times a, 1.0 times 10 to the minus 3 meters, quantity squared. We could cancel a 4 pi in the numerator with a 4 pi in the denominator. A 10 to the minus 7 cancels with a 10 to the 7. A meter squared in the numerator cancels with a meter squared in the denominator. The units we are left with are a Tesla coulomb per amp second, which means we end up with units of the Tesla. And when I plug this into my calculator, I get the value of the magnetic field at point C is equal to 5.7 times 10 to the minus 14th Tesla in the positive z direction.